Hello and welcome to another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 2, Lesson 8 on congruent figures. Now, this is an amazingly important idea because congruency is to geometry what equality is to algebra, all right? And it's kind of a weird word, congruent, all right? We're going to talk about what the word congruent means in this lesson right away. All right, and then we're going to kind of look at how we can tell whether or not two figures in geometry or two geometric objects, whether those are points, lines, rays, angles, segments, triangles, rectangles, etc., whether or not they're congruent. So let's jump right into it and just talk about what that word means. Here we go, congruent figures. Two geometric figures, i.e. points, rays, lines, segments, angles, triangles, polygons, etc. are congruent if they have the same size and shape. Put another way, one of them could be placed exactly on top of the other simply by moving it. All right, now this is again important. The idea is that if you took the geometric object, whatever it is, and you drew it on a piece of, let's say, tracing paper or something that you could see through, if you can pick that up and move it and lie it directly on top of another one of these objects so that they just completely overlap, all right? But you haven't stretched the object or anything like that, you haven't made it bigger or smaller or anything like that, then those two figures are congruent, okay? That's called mapping one figure onto another. If you can do that, then the figures are congruent. Now, some geometric objects are sort of like all of them are congruent to the same geometric object of the same class, okay? So we're going to get into that in exercise number 1. Let's take a look at it. There are many geometric figures that are all congruent to one another. Of the statements listed below, write down true or false. If you think the answer is false, explain why. All right? So let me just move that over there for the moment. Again, let's talk about letter A and figure out whether it's true or false. Letter A says all points are congruent to all other points. Well, that is a true statement. Oops, I lost my pen. Here it is, my pen. Anyway, so all points are congruent to one another. Imagine, having a point right here and another point down here, right? Are they identical? Yeah. They might be in different locations, but that's completely okay. The idea is if I took a piece of paper and I drew that one point on it, I could pick that paper up and lie it on top of the other point, okay? So all points are congruent to all other points? Absolutely true. No question about that. All right? Now, let's also talk about letter B. All lines are congruent to all other lines. So imagine you just had a line drawn on a piece of paper, with the two arrows at the end, and you had another line somewhere else, right? Would those two lines be congruent? Could you trace one line on a piece of paper, pick the paper up, and without sort of changing the size or the shape of the line or whatever, now you can rotate the line or you can reflect the piece of paper, you can shift it or things like that. Could that line then lie on top of the other line? And the answer is absolutely. All lines are congruent to one another because all they are is, infinite numbers of points that stretch out forever in two directions. So, yeah, all lines are congruent to all other lines. Now, let's take a look at letter C. All line segments are congruent to all other line segments. Well, if I had, sort of this line segment, and then I had another one down here, the question is, well, if I traced this on a piece of tracing paper and I brought it down here and I lied it on top of this one, would they be identical geometric objects? Would they just, completely and utterly line up with one another? And the answer is false, right? This would actually be a false statement, and the reason it would be false is because the segments could have different lengths. I'm going to just say diff. segments could have different lengths. Right? What I'd like you to do, there's only 2 left, is I'd like you to pause the video and think about whether all rays are congruent to all other rays and whether all angles are congruent to all other angles. Pause the video now and think about these 2. Well, all rays are congruent to all other rays? Absolutely, right? And the reason why, again, is that you could have this ray here, you could have this ray here, and remember, don't forget this is very important, rays extend forever. So even though I kind of chose to kind of stop this ray right here and put an arrow, and stop this ray right here and put an arrow, I could take this ray, put it on tracing paper or something like that. Maybe I have to flip it and rotate it a little bit, but I could then lie it on top of this ray, and even though the arrow might only come to maybe like right here, that doesn't really matter because the rays extend forever in that direction. So all rays are congruent to all other rays. Sorry, but I'm going to have to sneak this one in here. That's true. Now all angles are congruent to all other angles. That is most certainly false. All right. Right? And it's false for a very, very similar reason to why all segments are not congruent to all other segments, right? All angles are congruent to all other angles. That's false because the angles could have different degree measurements. Right? The plain fact is, let's say you had a right angle, right? And let's say you had an acute angle, like that. There would be absolutely no way that you could make this angle lie exactly on top of that angle because they have different degree measurements, right? They wouldn't lie on top of each other. You could make one of their rays lie on top of the other ray, but then let's say these 2 rays would not end up lying on top of each other. All right, so there are certain geometric objects, especially very simple ones, points, rays, and lines, that are all congruent to one another. And we don't really then talk about them so much in terms of congruency because really, who would care? What we really start to get into though is what makes line segments congruent to one another, what makes angles congruent to one another, what makes triangles congruent to one another, etc. More complicated geometric objects. So let's start to get into that in the next exercise. All right, exercise number 2. Line segment AB is shown below on the left. 4 other line segments are shown at the right. Use tracing paper. Circle which of the 4 segments are congruent to AB. All right, so it's very, very simple, right? Remember, the idea of congruency is that I could take this line segment and without making it larger or smaller, but certainly by turning it or flipping it or whatever, would it lie directly on top of any of these? Now, the best way to do this is by using something known as tracing paper. Tracing paper is any piece of paper that literally you can see through. All right, so for instance, this paper I can maybe not see very well at the board, but we can see through this paper. You can use patty paper for that. You can typically use even normal paper for it as long as it's not really kind of heavyweight paper, or you can use specialty made tracing paper that is literally transparent. For me, what I'm going to be doing is I just simply have another graphic that's sitting on top of here, right? So literally I sort of traced line segment AB out in red. So I can take this and I can kind of turn it and see which of these segments are congruent to it. What I'd like you to do right now is pause the video, trace segment AB onto your tracing paper, and then use it to figure out which ones of these segments are congruent to AB. Go ahead and pause the video now and go ahead and do that. All right, well this is a little bit probably trickier for me than it is for you, but let's see if EF and AB are congruent to each other. In order for me to do that, I've really got to take this thing and I've got to do a little bit of rotation with it as best as I can, right? And when I rotate it and look at it like that, what I can definitely see is that they're not the same, right? You can see that line segment AB was actually longer than line segment EF, so that is definitely not congruent to it. On the other hand, if I bring it down here to CD, whoops, and I get the proper rotation of it, I also see that CD is slightly longer. It's kind of hard to see, but CD is slightly longer than AB as well. All right, let me take a look at MN. Right, MN is exactly lied on top of, right? So AB, when oriented properly, lies exactly on top of line segment MN. So MN is congruent to AB. Let's take a look at line segment RS, our last one. All right, let's see. And as well, AB lies perfectly on top of RS. So line segment MN and line segment RS were congruent to line segment, whoops, AB. Okay? Now, we can come to a very simple conclusion about what makes two line segments congruent to one another. Exercise number 3. Fill in the following statement to make it true. Two line segments are congruent to one another if they have what? What's going to be true? What's going to make two line segments congruent to each other? Think about this for a moment. Well, they're going to be congruent if they have the same length, right? Because that's really all, that is the only distinguishing characteristic of a line segment, is how long it is, right? So two line segments are congruent to one another if they have the same length. And likewise, right, if they're congruent to each other, they will have the same length, right? Because that means that they can lie directly on top of each other. All right, let's keep going. Let's look at some other things, right? We can also talk about congruent angles. Now, congruent angles are a little bit trickier because an angle, of course, again, is a collection of just two rays that have the same starting point. So let's take a look at exercise number 4. Like all congruent geometric objects, one angle is congruent to another if it can be placed on top of it without changing size or shape. On the left is angle A. Using tracing paper to help, circle all other angles that are congruent to angle A. All right, now again, don't forget something that is extremely fundamental about angles, okay? No matter how angles are drawn, no matter how they're named or anything like that, an angle is a collection of two rays, and rays extend forever. No matter how short the ray is drawn, like here on angle E, that ray is very, very short, right? It's drawn very short. That's the way I should put it. But really, that ray actually extends forever. So just like with the line segments, what I'd like you to do is I'd like you to trace angle A off on tracing paper, and then just take that tracing paper, lie it on top of all other of the 5 angles to figure out which ones are congruent to angle A. All right, well, let's do angle B right away. That one should be easy. Let's take a look. I'm going to bring this thing right over here. I'm going to line up their vertices, and what I see, right, is that they are certainly not congruent to one another, right? Even though I can make these two rays lie on top of each other, when I do, these two rays do not lie on each other, so angle B is most certainly not congruent to angle A. Let's take a look at angle C, because that one's also kind of oriented in this nice way that makes it easy. And when I line them up, they do line up with each other. Now, if you're saying to yourself, well, wait a second, wait, no, they can't be congruent because this ray only goes to here and this ray goes all the way out to here, and likewise down here, no. Then you've actually missed the point with rays. Rays extend forever. So I guess the best way to look at two angles that are congruent to each other is, do they sort of fit together down here? Do you know what I mean? Up here, again, they extend forever. So it doesn't really matter how long I draw them because, quite frankly, I'll never draw them as long as that they actually are. So angle C is most certainly congruent to angle A. Let's circle that. Let's see if there's any more, right? So angle D is kind of oriented in a little bit of a weird way. So, you know, I may have to take my tracing paper and kind of rotate it a little bit to see if angle D and angle A are congruent to each other. But As long as I do it pretty accurately, I find that angle D and angle A are in fact congruent with one another. So angle D is another one. Let's take a look at angle E. Angle E really, at least on first glance, does not look like it's going to have the same measure. Let me again, it's a little bit difficult for me. But look at that, you bet. They completely and utterly fall on top of each other. So even though this ray of angle E is drawn smaller than this ray of angle A, those are certainly congruent angles. And maybe angle F is also congruent to it. I just need to kind of keep rotating this thing to see if they line up. And no, they don't, right? So even though I can get this ray, these two rays to line up, these two rays do not line up. So it looks like angle C, angle E, and angle D are all congruent to angle A. And that leads us again to a very natural conclusion that we saw with the segments, very similar with the angles. Fill in the following: two angles that are congruent if they have a little bit of bad grammar there. It should say two angles are congruent if they have what? So two angles are congruent if they have equal angle measurements, right? Or equal degree measurements. There we go. Equal degree measurements. And that kind of makes sense. It also tells you some nice things like, any two angles that are both 90 degrees, any right angle is congruent to every other right angle, right? Every 60-degree angle is congruent to every other 60-degree angle because ultimately speaking, they could be oriented so they lie on top of each other. Let's take a look at one last exercise. All right. Now, in the next lesson, we're going to concentrate exclusively on triangles. Triangles are probably, debatably, but probably the most important geometric shape that's out there. All right. So let's look at exercise number 5. Do the two triangles shown below have congruent angles? Trace triangle ABC and compare its angles to triangle EFG. Then, are the two triangles congruent? Why or why not? All right, so what I'd like you to do is take tracing paper, just like I have, trace out triangle ABC, and then use that to compare the angles between ABC and EFG to see if they have the same angles. Pause the video now and go ahead and do that. All right, now again, these angles haven't been drawn in that classic ray, right, where we have the arrows pointing out, but we can still easily look at it, right? Because if I take this triangle and I put it right up like that, then clearly these two angles must be equal, right? Because their rays are extending from that common vertex and they're overlapping each other. Likewise, if I take this and I move it down here, right, then I see that these two angles must be equal. Again, these two rays are overlapping each other. And finally, if I bring my triangle over here and my board cooperates, we also see that those two angles are congruent. So you bet, yes. Right, that's all we need there. So, I mean, if the three angles of one triangle are congruent to the three angles of another triangle, are the two triangles congruent? Pause the video now and put down yes or no, and then, regardless of which one you put down, give me an explanation for why. Well, the answer is definitely no, right? And there's a lot of different answers or explanations for why. One explanation is simply, one of the triangles is larger than the other triangle, right? So I could just simply say triangle EFG is larger than triangle ABC. Sure, they have the same angles, but the actual size of this triangle is bigger than this one. You could also say simply that when I used tracing paper, or when you used tracing paper, you couldn't get triangle ABC to lie entirely on top of triangle EFG. In other words, two triangles are going to be congruent if literally, if that red had covered the entire triangle EFG, well, then they would have been congruent. But they aren't, for a simple reason. This thing's too small. They have the same angles, but they do not have the same size. All right, let's wrap it up. Now, congruency is an extremely important idea in geometry. And again, I kind of started with this, and we'll look at it a little bit more in the next lesson. Congruency is kind of the equivalent of equality, right? We can say 5 is equal to 5, right? On the other hand, we can't really say triangle ABC is equal to triangle DEF. That really doesn't make sense because triangles aren't numbers. Numbers can be equal to each other, but triangles cannot, right? And so we come up with this idea of congruency. If I could literally trace one triangle out on a piece of tracing paper and lie it completely and directly on top of another triangle without stretching it or shrinking it down, then the two triangles are congruent. And that doesn't just go for triangles, it goes with points, lines, rays, angles, quadrilaterals, rectangles, etc. We're going to look at this more in the next lesson when we really burrow down and look more at congruent triangles instead of all these other congruent figures. For now, I'd like to thank you for joining me for another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.